this topic, we're looking at linear vector spaces and their operators. So the first space we're going to look at for a linear space operator is the null space, or the kernel of an operator. So basically, this is something that is an element in the input space that maps into 0 in the output space. So the vector x is in the kernel of t if t operating on x gives 0. The kernel is non-trivial if there is a non-zero x such that t of x is 0. The 0 vector is always in the kernel of t. Okay, so 0 in a linear operator, 0 is always in the kernel of t. 0 always maps into 0. Okay, so the kernel is trivial if only if 0 is the only element in that null space. Okay, so if you have something not 0 in the null space, then it's non-trivial. And the reason word trivial is used is because every element has the 0 vector in it. Okay, so that's trivial. Every kernel has that in there. So it's non-trivial if there's something other than 0 in there. Okay, if x is in the kernel of t, then for any scalar, that scalar times x is also in the kernel of t. So remember, the kernel is a subspace, and so all this is saying is that any element in that subspace is in the subspace. Okay, so any scalar multiple of that element in the subspace is also in the subspace. So well, let's move on to talk about a specific thing. I ask why, but I already have explained why, so sorry about that. All right. Suppose now our linear operator is a matrix A. So x is in the kernel of A if ax is equal to 0. Okay, again, the kernel is non-trivial if there's a non-zero x such that when I multiply A, I get 0. If x is in the kernel of A, then for any scalar, again, that is in the kernel of A. However, if x is in the kernel of A, now this is a significant thing that gives you some insight, some deeper insight into the kernel. The elements of x are the weighting values such that the linear combination of the columns of A is 0. So A times x can be written out this way, where A1 is the first column of A, AN is the nth column of A, and here I have a linear combination of the columns of A. Okay, and AX is equal to 0 means that this linear combination is equal to 0. That means this linear combination means that the columns are dependent. The only way you can get this linear combination being equal to 0 is if the columns are dependent. Otherwise, all of these guys, the x1 to xn, would have to be 0 if they were all independent. Okay, so that's one of the things that this equation shows, is that the columns of the matrix A must be dependent in order for there to be a non-trivial null space. So we've defined the range, we've defined the null space, and so we can actually talk about 4 important subspaces. The range, of course, is the column space. That is the space spanned by the columns, which is also the independent columns. The kernel of A is also called the null space, so we have that. The range of A adjoint, or A complex conjugate transpose, is sometimes referred to as the row space as opposed to the column space. This is the set of independent rows. And the kernel of A adjoint is often referred to as the left null space. So the right null space, I have A times x. I multiply on the right and get 0. Here, this is like multiplying on the left and getting 0. Okay, so it's often referred to as the left null space. And based on those definitions, we have these properties that can be proven. The perpendicular complement of the kernel of A is equal to the range of A adjoint. And so it's like, wow, these are really deep. These are deep properties, that the kernel of A perp space is the range of A adjoint. But you can go through and show, just based on the definitions, that these properties are so. And we have 4 of them. They're all kind of related. So this equation, for example, here, if I take the orthogonal complement of this equation, I get this equation. And these just give us the adjoints of those. So interesting. The rank of an operator. The rank of an operator T, we can think of it as the dimension of the image of the input space mapped through our operator. So that's equal to the dimension of the range of T. Okay, so, and based on that definition or that idea, we have this, what's called the rank nullity theorem, that says the dimension of the range of our operator plus the dimension of the kernel of the operator is equal to the dimension of the input space. Okay, not the output space, the input space. So generally, when we're working with matrices, we're going to be working with linear equations of this form, and which is basically related to systems of equations. So a set of equations that can be written into this matrix form. So we first look at these important operators, and the first important subspace associated with these operators is the null space.